Okay, welcome. This video should take you through curves in parametric mode, what parametric mode means to us, how we describe curves in this mode, and etc. So I'll read you the beginning here. So far we have described plane curves by giving y as a function of x. So what that looked like was, y equals some function of x, just like that, or x is a function of y. We've also written the relation between x and y that defines y implicitly, and so it didn't always equal 0. Perhaps it equaled another implicit, function of x and y. Some curves, such as the cycloid, are best handled when x and y are given in terms of a third variable, t, called a parameter. And we talked about this a little bit in Calc 1 when we saw, for example, the volume of a cone. And we studied related rates. So we studied how, if I have a cone and let's say water is leaking out of the bottom of this right circular cone, so as time is going on, since the water is leaking out, the radius is getting smaller, the height is getting smaller, and therefore the volume is getting smaller. But all three of those aren't necessarily changing with respect to each other. They were changing with respect to time. So remember, we differentiated this dv dt, dr dt, etc. So that was probably your first introduction to what we'll say might be a parameter, okay? And so t is time, is typical of a parameter, but doesn't necessarily have to be. So we'll talk about what that initial point and terminal point look like. I'll also show you how to get this on your calculator. But the parametric mode now is going to have two equations. One equation will say x equals a function of t, and the other will say y is a function of t. So two things are changing, not necessarily in relationship to each other, but in relationship to that third outside parameter, which is t. Please note, this is not necessarily three-dimensional yet. All this is t is kind of in the background, and t is helping us to calculate what our x and y values are going to be. So let me show you what I mean. If we have this equation here, x equals t squared minus 2t, that yellow highlighted equation can help me get all of these x values for this t chart below. And now notice our t chart actually has 3 columns to it because my input is now t. And when I input t in one equation, I'm going to get the x. And then when I input t in the other equation, I will get the y. So I'll do all the x's right now, and I'm just computing these by hand right now, putting them in this t squared minus 2t equation. So if I square the negative 2, I get 4. And then minus 2 times negative 2, so 4 plus 4 would be 8. And I keep doing that down. So negative 1 quantity squared would be 1, plus 2 is 3, 0 would be 0. 1 would be 1 minus 2 is negative 1. 2 would be 4 minus 4, which is 0. 3 would be 9 minus 6, which is 3, and t equals 4 would be 16 minus 8, or 8. So again, I put all those t values into that highlighted equation. Very simple, sort of plug and chug activity here. Okay, so now let's figure out the y's. So y is t plus 1. That should be a little bit easier calculations for me to do. So I'll go through here and do those. So if I put negative 2 in for t into the y, it's negative 2 plus 1 is negative 1, negative 1 plus 1, 0, 0 plus 1 is 1, etc. down the line. Now it's important to note that we are graphing still on a Cartesian plane. So we are still plotting points that are x comma y. So I'm on this Cartesian plane where my horizontal axis is still x and my vertical axis is still y. That is a very important determination to make because as you look at these points, you might not necessarily see each individual t value, but you will see the x and y plotted accordingly. So let me get a coordinate grid on here. And now I will plot my points. So I'm plotting the first point when t equals -2. So 8, -1. Again, plotting points like you've always done. 8, -1, 3, 0, 0, 1, -1, 2, 0, 3, 3, 4, and 8, 5. So what you can hopefully see is this is basically a sideways parabola. Let's see if I can make it work. Okay, that looks like so. I have no indication from what they gave me that this parametric equation would have a limited t value or a closed interval where t would be between 2 points, or two values. I have no indication for that, so I can assume that this trend or this sideways parabola would continue. One thing that a parametric curve has that a rectangular curve doesn't necessarily have on its drawing is we always put a direction on here. So I'm going to do this pretty boldly. I'm going to put a direction. So the first point, or the smallest t value that we plotted, was all the way over here at 8, -1. Then the next value, so as we increase t by 1, our graph actually went to the left, or our curve actually went to the left. And it continued going around like so. So parametric curves, when they're completed, have directions on them, and that says that in the problem. Sketch and identify the curve defined by the parametric equations, and then indicate the direction in which the curve is traced with arrows. So that's what it means. And then I do have a special note down here. Notice that the consecutive points marked on the curve appear at equal time intervals. And by that I mean all of your t values increase by 1. So these are equal time intervals as you jump from one time to the next. However, not at equal distances. So if you look between 2 points, I'll just point out this distance may be right here compared to, let's say, this distance right here. The two yellow highlighted distances are not nearly the same. However, they both have a difference in t of just 1. And that's because the particle will slow down and speed up depending on where it is in the curve as t will increase throughout your interval. So now let's look at this a little bit differently. Let's look at this as if it was a Cartesian equation, or putting this in our rectangular mode. So how could we eliminate the parameter? So let me carry down my equations in parametric mode. And we are going to do something called eliminate the parameter. And eliminating the parameter, people somewhat, there's kind of a one size fits all model, if you will, to doing this, and that they use substitution 100% of the time. And I'm going to show you throughout these notes today that that might not be the most efficient technique. But for this one, I think it is. So I would choose one of these equations to solve for t. I choose the y equation, so I will subtract 1. And I will substitute that y minus 1 in place of t into the x equation. And so t is y minus 1, so that will be quantity squared minus 2 times the t, which is y minus 1. Okay. And then I think because you can combine like terms, I will go ahead and multiply this all out here. So if I square that binomial, I get y squared minus 2y plus 1. And then if I distribute that -2, I get -2y plus 2. And I'll just quickly combine like terms. So x equals y squared minus 4y plus 3. And certainly for eliminating the parameter, I mean, you have 2 steps prior to it where you don't have any t's and you only have one equation. It's just x in terms of y, and that's fine. It didn't necessarily say that it had to be a function y in terms of x. In fact, this one's not a function, so that makes perfect sense. Now, in the past, if we gave this to you, you may not have known how to draw it. So sometimes these parabolas are more obvious, or these graphs, excuse me, are more obvious in Cartesian or rectangular mode. Other times it's much more obvious in polar or parametric mode, and you'll study polar mode in a little bit. I know that we all recognize, hopefully, y squared is a sideways parabola, but all the details of it you might have forgotten how to find. Okay, so what if I were to ask you to do the next part here? Redraw the picture if it has a finite interval. So now t is only limited between 0 and 4. So now what I'm going to do is look up my chart over here and only plot these points right here. And the t values kind of come with it, right? But meaning they're the behind the scenes calculation of these points, but I'm only going to draw the point 0, 1, and I'm just going to crudely sketch this here. Negative 1, 2, negative 1, 2, 0, 3, and see this is going to be way shifted up, but that's okay. 3, 4, and 8, 5. Okay. And I do need to make sure that I end at 8, 5. And I will label this 8, 5. I will label my horizontal axis X and my vertical axis Y. And my very first point that I plotted was 0, 1. So sometimes even if it's in the sky, I will make sure I label that. And so now I can answer the question here, what is the initial point and what is the terminal point? Well, I'm missing one important thing on this graph that, again, we cannot forget that parametric mode has a direction. So it's hard to know just by looking at this completed part of a parabola, if you will, which is the first point and which was the last point. We know because we have the table of values available, but really you need the direction that it traveled. So we know from looking from above that as t increases, this is the path that it takes. So these are the arrows that one might have on there. So that can show me, oh, okay, this 0, 1 is the initial point. And I'll put in parentheses when t equals 0. It's not necessary though. And the terminal point is where I end, and that is at 8, 5. And just in case you were wondering, that was at t equals 4. Again, there's your beginning, there's your end. Okay, so let's look at how to graph this on your graphing calculator. So if you don't have your graphing calculator yet, please pause this video and go get it. If you do, then hopefully you're ready to go. So the first thing I would like you to do is click Mode, which is right next to your blue second button. And we will probably see that you are in function mode. Okay, so if you scroll down, I'm in radian mode, which is good. I want to be in radian mode. And I'm in function mode right now, but if you'll notice right next to function mode, it either says on your screen para or parametric. So you'll want to arrow over to that and hit enter, and now you're in parametric mode. So now if you hit y equals, you will notice something very different. You now have an x1 and y1 according to t. Both of those have to be a pair that is input in order to graph the one curve. I'm using the color calculator, so I'll see it as blue. If I only put something in for x1, it will not actually graph anything because, again, I'm defining x in terms of t and y in terms of t. So it can't only plot the x values, for example. It's got to have both the x and y values plotted according to t. T is just, again, like that background piece that is being used to determine what x and y are. So I can say for ours, and now also if I hit this X button, it's X when you're in function mode, and it's in the same order that your mode was in. So if I click mode again, I can see it was function, parametric, polar, and then sequence. And so when I'm in this y equals, this X button will correspond to those modes. The first one is function, the T for parametric, the theta for polar, and the N for sequential or sequence. So I can hit the X button, it'll show a T, right? So the first one was T squared minus 2T. This is very slow for some reason. Minus 2T. And then I have to hit enter or arrow down to the Y, and I have to say that the Y value was T plus 1. And if I hit graph, if I ever can get there, okay, it looks good now. If I hit graph, you will probably notice that you only see part of your parabola. And there's good reason for that. If you hit window, you are in a very set window. And if this is not your first time in parametric mode, your window might not look like this. But if you hit zoom 6, which is zoom standard, that normally puts you in a negative 10 to 10 for X and negative 10 to 10 for Y viewing window. And that looks great. The problem is it's not necessarily what I'm viewing that I'm concerned with. I can always move that part around, but we have to make sure we're calculating the appropriate T values. So if you go to window, because remember, X and Y are dependent on T, so T is going to be really important here. So look at T min and T max. That's 0 to 2 pi. Well, that'd be great if we were in a trigonometry problem where we had T representing an angle, but T doesn't necessarily represent an angle. In this case, I have no notation that would say that. It's not sine of T or cosine of T, right? So I want to make sure, for example, what if we looked at T like we did our chart? So our chart, when we first started this problem, the smallest T value that we calculated was negative 2, and the largest T value that we calculated was 4. Now, if you wanted to see your T-step as 1, you can, and that will make it look a little bit more similar to what we did. However, it's going to look much more chunky because all it's doing is plotting the points that we have on our graph. So let me go back to our graph here for a second. It's only plotting that point, that point, that point, that point, that point, that point, and that point. And then it's just connecting them with a straight line. And so we won't necessarily see the really nice curvatures that we see in the fact that this should be, right, a sideways parabola. We see it a little bit more like linear little chunks. So I like to, in my window, keep my T-step really small. So I'll come back and change that in a second. The only, I guess, pro that I can see or advantage that I can see to keeping your T-step like this is if you really like the trace feature. So let's just say you graphed it and then you thought, oh, I forgot to pay attention to the order. Did it start up here at the top and go down this way, or did it go the way that we thought it went? Well, I can't tell if I'm just looking at a completed graph unless I go through the trace feature. So I can trace, and then this is counterintuitive. I want my cursor to move to the left, but your cursor is not based necessarily on an X value anymore. We used to move, if we wanted our cursor to move to the left, we would select the left arrow because we were decreasing our input, and our input happened to be X. So now I don't want to decrease my input. My inputs are T's. I can't go lower than negative 2, right? I can try all day long. It's not going to go anywhere because I said T min was negative 2. What I want to do instead is arrow to the right, because what that'll do is that'll increase your T by 1, or whatever you set your T-step to. So the benefit to having your T-step match what you wanted to draw is that you'll be able to see all your points. Here's your T value, here's your X and your Y value that you should also see plotted on your graph. That's one benefit. I like personally to keep the T value real small, so it can be something like pi over 24, or for now we're not in trig, so you don't have to have it in terms of pi. You can just keep it something like 0.1. That didn't work. 0.1. 1 or 1/10, right? And when you graph it, you should be able to see that it looks much neater of a curve, and I can see the parabolic curvature of it. And then the way I can see that is I can make sure in my table set, so second window, we should all have this set up to where we go to the independent variable and we select ask, because then that allows us to type in whatever we want for that independent variable. And then I can go to my table, and please don't panic. Your table is going to probably be empty because it's waiting for you to type in your independent variables, or t values in this case. So I can say, what is my point when t is -2? This is not behaving. I'm going to hit enter. And it'll tell me the x and y coordinate pair. I can do the same thing then when t is -1. I can do the same thing when t is 0, and you can go down your list and you can match your t chart to the values that you needed to find. So hopefully that helps a little bit with plotting some of those points. And if you did miss the direction, you can always get it back because you can arrow to the right after you click trace. Right, arrow to the right so it's going along your curve or increasing those t values. So looking back at your notes, I did give you a little bit of space to write whatever you wanted to about calculator ideas when graphing parametric equations. So what do you want your window to be? You might want to take a second, pause the video, and write that down. I don't ever recommend zooming because you lose control. The one thing to note when you zoom standard is to change your t values, right? So make sure you somehow make a note on there that you probably will want to, include some negative values for t. Otherwise, it'll default to that 0 to 2 pi. And then let's just make sure we're all in radians and not in degrees. So you may want to pause the video and take some other notes for yourself on the actual calculator. Okay, here's a question that does not involve the calculator at all, and really the calculator doesn't help you with this one. It's sketch the parametric curve given by the graph of the following parametric equations. So instead of me giving you the equation for x and the equation for y, I'm giving you the visual for x and y according to t. And then again, it's important to note that we're graphing this on a Cartesian plane where x is my horizontal axis, y is my vertical axis. So what I'm going to do is make this 3-columned t-chart. And I was saying t-chart, and I wrote x first. So I'm going to do it where it's t, x, and y. And I'm going to first only focus on what I will highlight here in yellow is this first graph. Okay, now we may know the equation for it. Let's not write it. Let's just go based on the visual that we see because we might not always know the equations for these. So what this says is your independent variable is t. So when t is -1, for example, your output is an x value. So when t is -1, your output, or x, is 0. So when t is -1, your output, or x, is 0. And I'm going to do that for a bunch of points on these curves. So when t is 0, for, again, x, it's down here at -1. And when t is 1, my output, or x, is 0. And I'm going to do one more here. I think when x is 2, and I'll star, when t is 2, and I'll star it, because this is kind of me extrapolating some data here, or some picture, just so I can get a really good image in my mind. 1, 2, 3, about. My x would be 3. And again, if it's off a little bit, that's fine. I just need to be able to match this or draw the shape of this parametric curve. So this will just help me do it. Okay, so then now my second graph is going to define y according to t. So I have the same sort of t values here. So when t is -1, and I know we probably recognize this as x cubed, but don't worry about it. When t is -1, the y value or output is -1. When t is 0, my function is 0. That means y is 0. 1 corresponds to 1. And again, Let's kind of guesstimate. 2 would be about here. This one's going to be a lot higher. And just so you don't think it's x cubed or t cubed, maybe it's, I don't know, 5. Again, we're making that up. Anything close would be similar, and I'll still see my curvature. Okay, so I'm going to draw this now on my Cartesian plane, and again, you're only plotting those points. Right here, 0, -1, -1, 0, 0, 1. And then, this is why I think it's somewhat important to keep going a little bit, is I can see, okay, 3, 5 might be up here. It just gives me an idea for what the shape might really look like. And again, if it was 3, 8, I would have even a much wider looking parabola that opens to the right. So what I can see is as t increases, you're going to get the direction. So we started down here, and then t went that way. So I can put my arrows on accordingly. And I had no reason to believe that these graphs were bounded from the beginning for x and y or t. They didn't have closed points for the beginning and end, so I'm guessing that they would have arrows on the end. Okay, so let's talk about eliminating the parameter, and let's really dive into a little bit of this algebra for this section. So what we're going to be doing is eliminating the parameter and writing this in a Cartesian equation, so where it only has x's and y's. So the first thing that I think a lot of you should do is go to your graphing calculator and say, okay, if I have these equations, let me move it off to the side so I can see both here, and I can type these in to my y equals. And what is important to note here, I did write 1/4 as 0.25, but you're still using this xt theta n button. You don't have to change your input to be t's or thetas or p's or whatever. It's just that x and y are now functions of some third or outside parameter. So you'll see a variable that is not represented as x or y. So that's the parametric mode. You're going to stay there, and when you hit that X button, it automatically does t's, and that's okay. That's kind of what we want. So now, again, I'm going to hit window before I hit graph, just to make sure that I'm going to graph some appropriate values here. In this case, t is an angle. So in this case, maybe 0 to 2 pi does make sense, right? So I'll change my window accordingly so that my t min is 0 and my t max is 2 pi. Ugh. And then your t-step, again, just make sure it's small, because 0 to 6 is not that large in the first place, so I'm just going to make sure that it's real small. And I'll leave -10, 10, -10, 10 for my viewing window just for a second here. And when I hit graph, I think we will find a shape that we all recognize to be an ellipse. It's very, very small. So what I would do in that case is go back and change my viewing window. So I might change my x's. I mean, those looked very small. So I might change those to be, for example, -2 maybe to 2, and that might even be excessive. I don't know, I might not need that much. And then the y's looked like they were a little bit bigger, but still not too excessive. So I'll just go something like -4 to 4. And again, you could look at your graph again and really calculate these, but I'm just going to get a little bit better of an image before I move on to the algebra. So there's my ellipse. Now, if I see that it is not a function, right? An ellipse is not a function. I'm not necessarily going to be too concerned with writing this y as a function of x, because it's probably not the case. Then it would have plus or minus, and it would have two equations to it, the top half and the bottom half. So I'm not too concerned with that. So when I see circles, ellipses, hyperbolas, things like that, I should know at least a little bit about conic sections to know that they are not functions. So let me give you your potential crash course here in conic sections. So I need to eliminate the parameter algebraically. So I am not going to solve for theta and then substitute it in here. If you do that, you end up with something like, and depending on which one you did, maybe I would have cosine of inverse sine of a over b, and I'm making up the a over b part for a reason here. And most of us don't know what that is. Well, trig of inverse trig is really just an algebraic expression. Let me show you why. Inverse means you're solving for an angle in a right triangle, which might look something like so. This means that this theta right here could be represented by inverse sine of a over b, and sine is opposite, so the a would be opposite, and the hypotenuse would be b. So I can use Pythagorean theorem to solve for my missing third side, and now I can take the cosine of this angle. Well, use your SOHCAHTOA or however you know it. So this is now adjacent over hypotenuse. And that's where we would need to end up, not at this mess up here. Okay, so trig of inverse trig is really just some algebraic expression. And again, that creates a lot of extra work for you, and I would not consider that efficient at all. So if you run down that path, I'm not saying it's wrong, I'm just saying it's perhaps not the most efficient technique. So let's look at what might be. We all should be familiar with one other thing. Cosine squared of, I'll use alpha, plus sine squared alpha, and you should already be saying it to yourself, equals 1. That's the most basic Pythagorean identity. We don't care what alpha is as long as it's the same in both cases. So what I'll say in this case is, can I solve these equations for cosine and sine and then just put them in there? Well, sure, I probably can. So, okay, I'm going to solve this, multiply both sides by 4 for cosine theta, or cosine 2 theta in this example. And I'll solve the y equation. I'll divide both sides by 2 to solve that for sine 2 theta. And now what I will say is, I know the Pythagorean identity of cosine squared, I'll just put an x or an alpha, you can put whatever you want, plus sine squared x is 1. And as long as those angles are the same, you can replace them with anything. So I'm now going to replace those with my angle that I have in my problem, which is 2 theta. So I now know cosine squared 2 theta plus sine squared of 2 theta is 1. And I know if 4x is cosine 2 theta, I can square that. So I have 4x quantity squared. And if sine of 2 theta is y over 2, I can square that to get sine squared of 2 theta. Now technically I've eliminated the parameter, but I'm going to help you out so you know how to draw these. So if I square to remove parentheses, it looks like so. And the ellipse and the hyperbola do always have to equal 1. The difference was one is a plus and one is a minus, right? So they face opposite or face together. And then again, technically I've eliminated the parameter, right? But I'm going to go one further step so that I can see it as x squared over something plus y squared over something equals 1. And just a refresher, or maybe some of you don't know this, but whatever is in my denominator underneath x, that is some quantity squared. So I move in the x direction the square root of that denominator. And then whatever is below the y, that looks like maybe a b squared, I move in the y direction the square root of b squared, or b. Okay, so I'll show you what that looks like here. And you can certainly Google ellipses if this isn't making sense. So I have x squared over 1/16, because again, instead of multiplying by 16, you can divide by its reciprocal, plus y squared over 4 stays the same, equals 1. So what happens is, in the x direction, you're going to move 1/4. In the y direction, you're going to move 2. and you're not shifting at all left and right because it's just x squared and y squared. Okay, so in the x direction, I move over 1/4 to the right and to the left. So these points right here are negative 1/4 and positive 1/4. And then in the y direction from your center, you're going to count up 2 and you're going to count down 2. And those 4 points are sort of the end points of my major and minor axes of this ellipse. So I can graph it that way. So again, I don't necessarily want to see the substitution because I think that your algebra will trip you up from time to time, but you have to make some relationship between your variables, what you have, and just turning them into x and y, so eliminating that parameter. And then the one last thing I would say is pay attention to the bounds that they give you. So if this one is from 0 to pi, I really want to take a look at it and see, okay, well, what happened here? So if I go to my window and I limit those t's from 0 to pi, but if I keep everything else the same, what would that graph look like? And it's still the same thing. So we're going to get into this later, whereas if I go from 0 to 2 pi, I'll actually see it trace 2 times. So if that's of interest to you, if you want to see it trace, which we don't necessarily need for right now, but we eventually will, you can arrow in your y equals screen over to the type of line, and you could hit enter on your type of line, and you can keep hitting enter on the old software, or if you're on the color one, you can go into where it has what looks like I call it a magnifying glass. That's what I call my Sherlock Holmes feature, because I'll show you what that's going to do. This is going to graph it and show you the line, but it's also going to put the little Sherlock Holmes, like a little magnifying glass feature on it as it goes around. So I can see it come around and complete one rotation, and then normally I can see it go around and complete the second rotation, but I can't in this case. I don't know why. I don't know what I hit. Maybe it didn't save it because this is being very slow. But in polar mode, when we get there, that's going to be very important as well. Okay, so just a couple other algebraic examples here. Here's one with E, and there's another one with E coming up. So I want to point out the differences between these two before I start them because they're pretty quick problems here. Again, if you graph these, they're going to resemble a graph that looks like this. And I should recognize that graph probably as a natural log function, maybe not as an E function, because I would have to reciprocate and reflect, reflect, not reciprocate. So I think if I graph it and it looks like natural log, maybe this is the better equation to solve for t and eliminate the parameter using substitution that way. But if you'll notice down here on the next example that we're going to do, x is a function of t but with an e, and so is y. So we're going to approach this one a little bit differently than the first one. So again, I have two options truly to solve for t. A lot of people start with the easiest path of, oh good, excuse me, undo, y minus 1, I shouldn't be talking and writing at the same time, y minus 1 is t, and then they take that y minus 1 and substitute it in to the x equation for the t. And technically, you have eliminated the parameter. But if I ask you to take that equation that is in rectangular mode, it's based on x's and y's, and if I asked you to graph that, I'm not sure you would be comfortable in doing so. So I don't know that that really gave you the information that you were looking for. So while that is correct, I don't know that that would be my method of choice here. Since I know maybe I've graphed it in parametric mode and I know it looks like a natural log curve, I'm going to take this x equals e to the 2t, and I'm going to use my natural log properties to solve for t in this equation. So let's take the natural log of both sides. My exponent can come down in front, so 2t times natural log of e. Natural log of e is 1, so then I can just divide both sides by 2. Now there's another way to write this. It is 1/2 natural log of x, so it's whichever one you're more comfortable with. And then I'm going to put that into the y equation. Y is t plus 1 according to my given parametric mode. So y is 1/2 natural log of x and then plus 1. And I do know how to graph that because natural log function has a vertical asymptote at 0, so this still would have a vertical asymptote at x equals 0 because just shifting it up 1 does not move the vertical asymptote. And then it looks something like so. Shift it up 1 and has a vertical shrink, if you will. Okay. And if we need to find points, I guarantee that we can plug in values and find some points. I'm not too worried about that. Okay, our last major example here is x equals e to the 2t and y equals 3e to the 4t minus 1. So this will look a little bit similar to the one you previously did, although this one is actually going to be a little bit more friendly. So what you'll notice, I hope, is that in this first equation for x, I can actually rewrite y so that I see this value of e to the 2t inside of this equation for y. So what I mean by that is if I rewrite y to be like so, where e to the 4t is actually e to the 2t quantity squared, because then what I'm recognizing is that this e to the 2t is the same as that e to the 2t. So really, I'm just graphing 3x squared minus 1. So I know exactly what this looks like. Okay, and again, I could certainly use natural log and do it the same way that I did before, solve all the way for t and then substitute that in. I would just have to make sure that I'm very careful with my natural log properties. But one really important thing to note about this one is that no matter what t is, positive or negative, when you're raising e to a positive or negative value, that output then is always going to be positive. That is exponential growth. So if we take a look at e to the 2t, for example, looks something like so. It will always be positive. It will never ever be 0. So naturally, we're going to have a domain restriction here. And so what I will say is that x is going to be greater than 0. And so when I draw my parabola, I'm actually only going to draw the right-hand side of this parabola. So it is down 1 vertical stretch by a factor of 3. And I'll have my arrows on there because it's parametric mode. So as t increases in my parametric equations, my values for x and y will also increase. And again, this is me graphing this on a regular Cartesian plane, but it is important to note that even though you're graphing this parabola, you do have a domain restriction. And also if you graph this in your parametric mode in your calculator, you will see only half of that parabola, just like I have there. Okay, and then one last thing for 10.1 parametrics. There's just some fun graphing, if you will. So there's a cycloid. The cycloid is as you trace out a point P on the circumference of a circle, so that point right there, as the circle rolls along this straight line. So as it rolls and rolls and rolls and rolls, this is what you're going to get. Okay, and it bounces and keeps going. Okay. So depending on what your radius is of your circle, these are the parametric equations that you will have. And one of the first people to study these was Galileo, and he proposed that bridges be built in this shape. And he was trying to find the area under one arch of these cycloids. So you can graph this cycloid if you want on your calculator. That's the cycloid with radius of 1. And then this leads you to some other fun graphing if you want to take a look at some other fun pictures. You can play around with that. I hope you found this introduction to parametrics helpful.